Every relation is associated with a unique other relation called its inverse. And the inverse of a relation is just the relation that we get if we take our existing relation and reverse the entries. We indicate the inverse with the superscript -1 notation, and when we name the inverse function, we read this symbol as R inverse. Right, so the superscript -1 here should be read as inverse. It looks like an exponent -1, but it is not. It's indicating that we're taking the inverse relation. So just to practice this concept, we've got a couple of simple relations here, and we're going to find their inverses. How do we find their inverses? Well, we just reverse the order of the input and output. So here I have -9, 1. Reversing that order, I have 1, -9. Here I have -5, 1. Reversing that order, I have 1, -5. I have -2, 9. Reverse that and we get 9, -2. -2, 8. Reverse that, we get 8, -2. So we just reverse the order of all of the pairs. -9 was related to 1 before with relation R. With relation R inverse, 1 is related to -9. You can think of this as something like father and son. If A is the father of B, then B is the son of A. Those are describing the same relationship, but the orders are reversed. That's what an inverse relation does. So just to see one more example, S we have -2, -3. That reverses to -3, -2. We have 4, 4. Oh, there the order doesn't matter. We have 6, 8. That reverses to 8, 6. We have 6, -5. That reverses to -5, 6. When we reverse the order in our pairs, we're also going to exchange the domain and range. The domain of the given function will be the range of its inverse. The range of the given function will be the domain of its inverse. So suppose we have a relation in which the domain is the numbers 1, 3, 5. The range is the numbers -2 and 2. If we want to find out the domain of the inverse, well, that's the same as the range of the given relation, which we were just told was -2, 2. The range of R inverse, well, that's just the same as the domain of the given relation, which we were just told was the numbers 1, 3, 5. So when we reverse the orders of the pairs, that also reverses the domain and range. Here's a couple of places we're going to apply that. So suppose we have the function f of x is x squared restricted to x being positive. So the domain of f, we're being told right here, consists of values of x such that x is positive. Or we can write that as the interval 0 to infinity. The range, then, of f inverse has to be the same as the domain of f. So that's also 0 to infinity. Or in other words, the set of positive numbers, and 0. So because we know the domain of f, we automatically know the range of f inverse. One more. Here's a situation that we're going to encounter later, where we know the domain of a function and we know the domain of its inverse. Using that information, we can figure out the range of the function and of its inverse. The range of the function is the same as the domain of its inverse. So that's this set. It's the set of x such that x is not -2. The range of the inverse, that's the same as the domain of the original function, which we've been told is the set of x that are not equal to 4. So there are various ways that we can use this fact that taking the inverse exchanges the domain and range. We can use it when we've restricted the domain of a function. Well, that's going to tell us the range of the inverse function as well. Or if we have a situation where we know how to easily find the domain of a function, and we know how to easily find the domain of its inverse, that can let us figure out the ranges of those functions if they're not readily apparent.